Welcome to the Spring 2020 capstone presentation for Project Coeus. Personnel involved in this project were Mark Holloway, James Campow, and William Strawn. The presentation will be delivered in three basic sections: the introduction, covering the background, analysis, motivation, approach, and modeling descriptions. The second part, the solution, will cover technical details, model history, final model, and tools. And the third part, the conclusion, will cover requirements, model the data flow, accuracy, and the conclusion itself. Let's begin. Student retention and graduation is a common topic of concern among higher education institutions. Every institution wishes its new students to continue on year to year, and it's measured as retention, and graduate in a timely manner. At SOU, faculty, advisors, and the Student Support and Intervention Department attempt to identify and offer assistance to students who may be at risk of dropping out or are having trouble graduating. Unfortunately, reasons students drop out vary and are often unpredictable. By the time SSI can get to a student, it may be too late. In an effort to meet those needs, the Institutional Research Department, IR for short, at SOU developed a model to predict the likelihood that a new student will retain based on logistic regression, which, although it works, presents obstacles, and there are better methods to achieve these results, which we will discuss later in the presentation. The current model takes a new freshman who enrolls at SOU and assigns a retention probability index, RPI, to that student. An RPI ranges from 1 to 10, 1 being unlikely to retain to the next fall term, and 10 being likely to retain to the next fall term. The list of new students and RPIs are forwarded to SSI, who offers support to high-risk students as appropriate. Resources are finite at educational institutions, and focusing the limited budget and manning is vital to the health of the continuation of SOU, and more importantly, providing opportunities for students to excel in life. There are, per the SOU Factbook, currently 4,977 undergraduate students at SOU, with roughly 3,380 being full-time. Currently, 1/3 of all incoming freshmen are not retained, equating in 2019 to a loss of 648 students, which in financial terms, just accounting for tuition and fees only, is a loss of over $5.5 million. Needless to say, financial reasons are not the only motivation behind producing a more accurate model, but it can be of great value to all. Our first big decision on this project was how do we approach this problem and improve upon what is already in use. We started with two hypotheses, which influenced our decision in arriving at a solution for our client. One, there exists a correlation between the provided student data and student retention. Our second was that there is enough data for a given student to reasonably predict retention for that student. The first technique we considered was linear regression, machine learning, but the drawback as it considers normal distribution of dependent variables, and it's basically all about fitting a straight line with your data. We next examined the logistic regression model, which is the one in current use. The model in use only supports first-time, full-time freshmen and uses a technique called logistic regression. Mentioned earlier, logistic regression is likely the most commonly used algorithm for solving all classification methods. The main problem is it's binary, or in other words, a black or white, no gray scenario. Is someone in a court trial 100% guilty or 100% innocent without a retrial? The law says they are, but who on the jury knows the full truth or is allowed to give a 30-70 vote? Suppose you are monitoring sales. If the person buys, a 1 is scored for them. If no sale, a 0 is scored. That does not tell you that the person did buy the article, but not from you. It does not tell you that the person also did not buy that item at a slightly cheaper version or smaller quantity than you were offering. Same can be applied to college students. Because SOU doesn't retain them does not mean they did not go someplace else to finish or come back a few years later. I will now turn the next portion of this presentation over to Mark to explain more in depth our solution.
Logistic regression is great if you understand how all of your data directly impacts the thing you are trying to predict, but these relationships are not always obvious. Suppose a student is receiving a scholarship, but also a full Pell Grant that scholarship may mean less, and even less if they're pursuing a master's degree. So what we would like is for our machine to take into account these sorts of relationships that aren't clear. And we can do that by taking our student data cubes and our actual retention numbers and giving them to a computer, asking it for a machine that can make really nice prediction patties for us, and the computer will give us a meat grinder, the optimal tool for producing prediction patties. And so what does our meat grinder look like? Well, it's simply more logistic regressions stacked on top of each other that through the computer's construction of that meat grinder, it tunes this itself until it has something that makes great predictions. And so what do our data cubes look like? They're 130 parameters, 130 over every single year that the student attends. So for a 4-year degree, 4 years times 130. Some of these values are from before the student attends. Some of them are updated over the course of the year, such as performance in classes and further monetary awards. And then our meat grinder is a series of 2 neural networks. The first neural network attempts to predict how long the student will attend throughout their entire program, and our second network is the actual classifications. Both networks intake mostly data from freshman year. And so this charts some predictions and compares them to the actual retention data we have. Our x-axis being the output, our prediction patties, and the y-axis being the number of students in each of these buckets on the x-axis. The buckets are all 0.05 wide. So for example, the first black arrow is pointing to a bucket of 150 students between the ranges of 0.65 probability and 0.7 probability. It has gotten wrong 50 students, the red students, we know not to be retained, and 100 students we know to be retained. As we carry this group of 1,700 students through to the next 2 slides, we would like to see the blue move to the right and the red move to the left as our models become more accurate. This is the current logistic regression model that the institution uses, and this is the model we developed during our first capstone session. Between the 2 arrows, you can see the bounds of intervention that the institution has defined for who to contact for interventions. We've significantly reduced the amount within these bounds due in course to our model becoming more accurate. And then within Capstone 2, we've significantly divided these 2 groups up with a collection of very accurate results on the right. And here are our 3 models compared to each other. The tools that we used were Coeus for our neural networks, Talus was excellent for hyperparameter tuning, and Fancy Impute for k-nearest neighbors imputation.
Thank you, Mark. Using these tools and ideas, we needed to provide at least 80% accuracy, and in the long term, we wanted to see an increase in yearly student retention. Our software requirements were to build a compact Python script. It needed to be modular. I'll get to more on that in a moment. The Python script needed to clean the data we received from SOU and implement a neural network that improved upon the accuracy of SOU's current logistic regression model. So under the hood, what our software does is it takes a CSV file that has been formatted by SOU, their student services, The script takes that file, it cleans data off of the CSV. So this replaces any alphabetical values with numerical values so that our script can further read it. Our script then imputes any blank data values, so it estimates blank values using logistic regression. And then that data is input into our first neural network. So the first neural network takes our cleaned and imputed data, and it outputs a prediction on the number of years that the student will be at the institution. The second neural network takes the output from the first neural network, so those number of years, and also the second neural network takes our imputed data. The second neural network uses this data and classifies each student in the CSV file as either retained or not retained, and then also outputs the confidence of that classification for each student. And we use this as our probability for retention. So comparing accuracy to our current for our current model to previous models, logistic regression had about a 78% accuracy. So accuracy is correctly classifying students. The logistic regression had an accuracy of about 78%. Our version 1 had an accuracy of about 84%. And our version 2 has an accuracy of about 94%, which is quite a substantial improvement. The impact of our model: it will provide better identification for intervention candidates by limiting the number of false positives in that 40% to 60% retention probability range. So the students that the model is most unsure about. This helps SOU by making sure they don't intervene on students that will be classified as positive, which has been shown to negatively impact academic performance. And this will also save on work hours, making sure that interventions are only done on students that need to be intervened upon. This will in turn improve intervention successes and reduce intervention failures. In conclusion, our model's accuracy indicates a correlation between data and student retention, and the amount of data we received is sufficient to reasonably predict student retention. Our 94% accuracy demonstrates this. Our metric will provide SOU staff the tools to make more informed decisions upon whether or not to perform student interventions. Thank you.